Atmospheric chemistry might be a relatively weak forcing or feedback process. Nevertheless, there are a number of important issues and probably very interesting issues to be investigated. And I can see now that most groups in the world are looking at these possible interactions and are even considering putting a relatively detailed chemical scheme in the future climate models. So why should we add, or where are we considering adding chemistry in general circulation model? Of course, it is to assess the effect of changing atmospheric concentration on the climate system, especially here the effect of reactive gases, which I will discuss. But I think very importantly also is to look at how changing climate might affect the chemical composition of the atmosphere, in particular air quality, things like surface deposition. So from my point of view, and probably you'll see that a bit through the talk, the reverse effect is even more interesting than the direct effect or the forward effect of chemistry towards climate. And in fact, the two cannot be dissociated. So basically, we have to look at the climate problem, the natural forcing, maybe the greenhouse gases here. But then what about the emission of reactive gases on air quality, and how does air quality change affect climate change? Now, I think this view graph comes from Dan Albritton at the Aeronomy Lab, where he was just asking where atmospheric composition fits in. And he says much of the coupling between incoming solar energy in the atmosphere occurs via trace constituents, so they should be taken into account. And this coupling here leads to some relatively important, major, in fact, environmental issues, ozone layer depletion, and hence greenhouse gas effect. And of course, changes in trace constituent arise largely from human activity, surface emission, and so the regional air quality issue is kind of linked to that. Now, trace gases do not only affect radiative forcing. You see here a number of compounds, CO2, methane and CO2, the greenhouse gases are there, or the major greenhouse gases are there. They lead to direct effect, but you can have indirect effect also. Basically, that can happen via aerosols, and you can see that as we talk about aerosol, the chemistry of reactive compounds becomes important. Of course, the atmospheric chemistry community is also interested in things like impact on ecosystems, which, by the way, can feed back into the climate issue, and also impact on health. That's especially the issue of air quality. And you see a relatively complex table here with different type of direct and indirect effects. So what I would like to do then is to talk about, first of all, the forward aspect, the impact of changes in chemical composition on climate. Then I'll say a word about the impact of climate change on chemical composition. Then I'll try to see that they have to come together. So we'll talk about feedbacks or interaction. And then if we have time, I'll try to say a few words about integrating atmospheric chemistry and biogeochemistry into broader and more comprehensive Earth system models. So let's start with the impact of changes in reactive gases on climate. And of course here we have to recognize that trace constituents have a radiative impact very often, but they indirectly also can trigger changes through changes in the circulation or in the hydrological cycle. We have to deal, of course, with the well-mixed greenhouse gases, which I will not describe in much detail, and I will not talk at all about CO2. We have to deal with stratospheric and tropospheric ozone, and we should deal with aerosol particle, but that was discussed by Phil, so I'm not going to talk about this. So if we talk the well-mixed greenhouse gases and look at their relatively weak interaction with atmospheric chemistry, we first have carbon dioxide, which is completely insensitive to chemistry, except perhaps in the upper atmosphere where it photolyzes and produces carbon monoxide. If we look at methane, then here we see that the loss of methane is associated with the destruction with the OH radical. And once we talk about OH, we plug in a very complex chemistry. And here we have certainly a link. Now, luckily, the lifetime of methane is of the order of 8 to 10 years, so the effect is relatively slow compared to many other compounds in the atmosphere. If we deal with nitrous oxide, another well-mixed greenhouse gases, it is not destroyed by chemical reaction in the troposphere, but once we get into the stratosphere, it is photolyzed, and a small fraction of it is really destroyed by a reaction with the electronically excited oxygen atoms, which is produced from ozone photolysis, and that leads to the production of NO, which is the major source of ozone destruction in the stratosphere. So here we have a bit of a link between, well, this compound introduces a link between the climate issue and the stratospheric ozone issues. And the same is true for chlorofluorocarbons, which are also very long-lived but destroyed by photolysis in the stratosphere. So the OH radical is very important as we start to think about, for example, OH, but also many other compounds. Some compounds react very, very rapidly with OH, and these might not be well-mixed greenhouse gases, but they might have an indirect impact on the chemical scheme, so we'll have to say a word about it. We already talked about terpenes, about isoprene. They all destroyed by OH, so OH is key. It is the major oxidation agent. And here are the reaction of how basically OH is formed. We start with the photolysis of ozone at short ultraviolet wavelength. The O single D mostly, in fact, I probably have another. Yeah, most of the O single D is quenched down to atomic oxygen, and this oxygen atom then goes back to ozone. So basically, this is a null cycle in perhaps 97% of the cases. But once in a while, O single D doesn't collide with any other molecule, but it collides with water vapor. In that case, it's not quenched down back to the fundamental atomic oxygen and back to ozone, but it produces OH. So this is how OH is produced. This is the primary OH formation. There are other mechanisms that have been identified recently associated with the release by the biosphere in particular of a number of organic compounds like acetone or some aldehyde. They move up into the upper atmosphere, especially in the tropics, and they can be photolyzed there and produce also OH. So it's more complicated past this. So this is a distribution of OH in the zonal mean, and you can see that the largest concentration are in the tropics, and the tropics is really the region where photochemistry is important and where compounds like methane, for example, will be most efficiently destroyed. Now a word about ozone and climate. And ozone reacts, interacts with climate, first of all, because it absorbs solar ultraviolet radiation, mostly in the stratosphere. So there is a heating mechanism, the major heating mechanism in the stratosphere is associated with ozone. But it's also a greenhouse gas and therefore has a contribution to the greenhouse effect, especially through the amount of ozone that are found near the tropopause region. Now, the ozone depletion that we have seen in the stratosphere should therefore lead to a small cooling, while tropospheric ozone increase leads to warming. And so, as we, this is, okay, it's not my microphone. So, as we deal with ozone in the troposphere, we have to consider a relatively complex system. First of all, we have some input, downward motions of ozone from the stratosphere. Remember that 90% of the ozone is located in the stratosphere. Some of it gets into the troposphere, but we have also local production through a number of radicals that are coming from a number of sources, and here are some of the sources of these radicals. Some of them being potentially induced, well, changes being induced by climate changes. There is also, for example, production of NOx by lightning, and lightning changes could also be associated with climate change. But the chemistry here is associated, of course, with temperature and humidity, climate, and also by transport, weather patterns, and so on. The removal of soluble constituent is also an important aspect, both the dry deposition, but also the wet removal by scavenging, which might happen soon. So basically, as we look at ozone, we start with a number of processes in the stratosphere, and stratospheric-tropospheric exchange, the transport. We look at emissions of a number of ozone precursors, water vapor, carbon monoxide, nitrogen oxide, those two very, very affected by human activities. Lightning, as I mentioned, maybe emissions by airplane, and that's basically the system that we have to model, and it is a complex system to model, as I will show you. This is just to remind you that the destruction of ozone in the stratosphere, which should be included in climate chemistry model, involve, of course, a number of catalytic reactions that are related to the presence of compounds like nitrogen oxide or chlorine, also affected by human activities. I'm not talking here about the additional mechanisms that affect ozone at high latitude in particular that create the ozone hole. I'll pass this. This is an important curve for those who are trying to understand how ozone is produced in the troposphere. And what you see here, this is for summertime surface conditions, is the net ozone production as a function of the level of nitrogen oxide that is present in the background atmosphere. And this is, if you want, a kind of a representation of the degree of pollution. If you are over the ocean, for example, where nitrogen oxide is very, very low, basically the net chemical effect is, the chemical production is negative, so ozone is weakly destroyed, but that happens over a large region of the world. If you increase NOx, in other words, if you enter in a region that is weakly polluted, you can see a strong dependence of the production to the level of NOx. In other words, the ozone formation is highly controlled by the level of NOx, and also you go from a negative situation to a positive situation with a maximum here. Then as you go to extremely polluted region, like in the middle of an urban area, you titrate really ozone by the NOx. The NOx is as high as ozone, and you have a number of reactions. You convert nitrogen oxide into nitric acid, and so you go back into a situation where the production gets negative. So models, chemical transport models exist and are able to account for all these processes, and Jean-François Lamarck, for example, has been working here very much on these type of models. And basically what you recognize is that you have hotspots of ozone concentration at the surface, weak concentration over the ocean because we are in a region of net destruction, and the production that we see mostly over the continent occurs in regions where the precursors are important. Nitrogen oxides in particular, which are largely produced by combustion processes, namely industrial regions or biomass burning. These are regions where ozone can be important. So the models today are able to reproduce these kind of patterns. These patterns are also evaluated by satellite observation, and generally speaking, with some exceptions, of course, perhaps in heavily polluted regions, the models are doing a job that's sufficiently good that they could be used for climate, for example, simulations. Now, as we look at the trends, first we can go back to the past, the historical ozone change, and we have some observations to guide us. Now, how accurate these early observations are is, of course, a big question mark, but these are observations here in Europe, different altitude, so mostly in the Alps, in the mountains, Jungfrau Joch here is the highest point. You see the level of ozone being here, near the surface perhaps around 20 parts per billion. And if you look now at the most recent observation, you see values that appear to be roughly a factor of 2 higher. That's a relatively large change, sometimes even more than that. And so if you try to represent this in a model, you have, of course, to make a large number of assumptions in the emissions that you're taking. But simple calculation that you can do is you assume that the pre-industrial situation didn't have fossil fuel emissions, and that the only emissions of precursors were coming from lightning, from soils emissions, from vegetation emissions, and also from biomass burning. And here the question is, what was the biomass burning emission at that time? Most models assume it was lower, much lower than today, but we heard a bit earlier that might not be the case, and I think that's a major problem. So when you look at the difference between, say, present and or pre-industrial and present, you see this is a zonal mean situation for January and for July. You see relatively large changes, especially in the summertime when solar radiation, therefore photochemistry, is pretty active. What is 100% is in this greenish, so you see about a factor of 2 or even more at the surface in the most industrialized region. But you see also an influence all the way to the tropics, where this has an impact that is important on the radiative forcing. Now, as we look into the future, yes, sorry.
Which direction, if North American grass, there was a lot more biomass burning in North America in pre-industrial times, which direction would that take the ozone?
Well, the biomass burning should produce ozone. So if you have less, we should decrease, which, is an interesting hypothesis, and I don't think it has been well treated. One of the issues, of course, is as we calculate the changes to know what we had in the pre-industrial time, and the data, that we have a lot of data, but these data were done around 1900 using some papers that were changing color depending on the level of oxidants. But of course, ozone is not the only oxidant, first of all, so those measurements can be very uncertain. And also these measurements were very perturbed or affected, let's say, by the level of humidity. So nobody knows exactly. But the general feeling, especially if you look at the key station of Montsouris in Paris, it's a park in Paris, showed value of typically 10 to 20 ppb at that time, if you believe them. And they have been reanalyzed in detail, so there are a lot of people who believe them, compared to perhaps 40, 50, 60 ppb today, when you don't have a big episode that leads, like a few weeks ago, Paris had 150 ppb during the heat wave. Yes?
Quick question. The big difference seems like in the summer at temperate latitudes. Is
That's
that
right.
interaction of the photochemical effect with the emissions?
That's right. You need emissions, NOx, CO, hydrocarbons, and you need high photochemistry. You will see that in the future it might be very different. So now a number of people are trying to look at scenarios for the future in the emissions of reactive gases, not only on the greenhouse gas, but reactive gases. This is here an example, I think that's a document from YASA, showing the anthropogenic emissions of NOx as predicted beyond 2000. And you see the IPCC scenario showing a relatively large increase. Another scenario here, which is based on current legislative, what is it?
Current legislation.
Yeah, current legislation shows less increase. And then people have been looking at the so-called maximum feasible reduction and have been running models based on these new scenarios. These are, again, scenarios for global methane emissions. We'll see how long we can sustain this. I believe that one of the major uncertainty for prediction of the state of chemistry and maybe also impact on the climate is really to know what's going to happen with methane in the future. We know that 20 years ago the methane increase was 1% per year. It is now 0% per year. We don't quite know exactly why. We might have some ideas, but we might not know exactly. And what's going to happen in the future? It could be a flat situation, could be a dramatic increase. I think that's an open question with a lot of consequences of anything we can predict. In fact, I'm going to speak loud. These are here for certain compounds. The percentage change in the emission, anthropogenic emission in 2030, showing you the A1B scenario, the B1 scenario, the current legislative scenario, and the maximum feasible reduction. You can see that these scenario can be very, very different depending on the constituent and the scenario you are using. So based on the CLE scenario here and looking at the situation in 2020 compared to present, this is the change in surface ozone. And what is interesting is that this particular model shows a large increase here in India based on that model. And what is interesting also is that the changes that you see in the Pacific and Atlantic in the Northern Hemisphere are mostly due to ships and ships operation. I think, Peter, you should come in because you're going to. I know you're still under the roof there. Okay.
Could you speak louder?
No, my microphone doesn't have loudspeaker. I can try. Okay. Now, taking the same model as the one you saw earlier, and looking, this is an old scenario, the IS-92A scenario. We try to calculate what would be the ozone level around 2050. And this is again the zonal mean between the south and the north poles. And you see that the future change in ozone appear to be mostly located in the tropics as opposed to the Northern Hemisphere. There are several reasons for that. What? You're laughing because one of them is because a lot of the emissions growth should be taking place in South Asia. The other reason is that in the Northern Hemisphere, even if we were to increase emissions, we are to a large extent in the saturation zone. We have reached that saturation zone, and doubling NOx emissions would not create a lot of increase in ozone. We are already at the maximum possible. This is now the mean radiative forcing calculated between 2000 and 2100. This is an average of perhaps 15 chemical transport moles, showing that indeed in the future a lot of the forcing produced by assumed ozone, I think this is the A2 scenario, would be mostly in the tropics with value that could be reaching about 1 watt per square meter, which is not necessarily a very small amount compared to CO2 at the present time. And it's, what? That's a global average. For the global average for that, I don't remember what, but it's probably about, it's less than 0.4, I think. It's been 0.4 in the past to now. That's a bit less, but Now, I have to regenerate my voice a bit. The point I want to make here is that we can wait 10 minutes, huh? Maybe we take a break.
Contemplate this ozone issue.
What?
Contemplate the ozone issue while we take a break.
Okay. So the point I wanted to make here is that even if you do not, if you do not consider the chemical scheme in the mole, and you want to look, for example, at the radiative effect of methane, for example, Joe Schindel gets, I took this number for me, 0.6 watt per square meter. But in fact, if you include the chemistry and in particular the increase in ozone that has been produced by the methane increase, you have to add another 0.2 watt per square meter. And if you look at the past, this is about half of what the CO2 forcing has been. So it's not negligible. If you have an increase in methane, it will also affect OH because methane reacts with OH, and that will have impact, for example, on the conversion of SO2 to sulfate. And here we have a link between gas phase chemistry and aerosol, and that could also then have potential radiative impact. Just a word about gas phase compounds and aerosols, just to say that some gas phase compounds can be converted to aerosol. You heard it from Phil. We start very often with the DMS, which is an organic compound that's emitted by the ocean. It is converted to SO2 by OH, and then SO2 is further converted into sulfate by other species like H2O2 and ozone. So you can see that knowing the composition and its evolution might have an impact on the calculation of the formation of the aerosol. Another example is provided by the oxidation of biogenic monoterpenes, also perhaps isoprene, which produce organic aerosols. So there is a connection here. This is where perhaps chemistry could play an important role also in the climate business. But on the other hand, of course, you have to remember that the aerosols themselves modify the penetration of solar radiation, and therefore the photolysis of a number of chemical compounds. And in addition, of course, aerosols provide sites for chemical surface reactions, both in the troposphere but also in the stratosphere where, for example, chlorine is activated on the surface of sulfate aerosols or ice particle and are the source of the formation of the ozone hole. Yep.
I'm curious how important that last effect is. If you did the tropospheric chemistry with current aerosol and that radiative shadowing, and you took away the sulfate. I mean, is that a 10% effect, a 30% effect? 2%?
On the chemistry.
Yeah, on say ozone concentrations.
Yeah. It's not a very terribly important effect, we believe, and Daniel Jacob has done some work on that. We have done some work on that. What seems to be a potentially important problem are the reactions on the surface of elementary carbon, black carbon. And all depends if it's hydrophobic or not. And there are still uncertainties in some of the lab chemistry that you cannot come to a very definite answer. But the general belief is that this is an effect that is probably less important than the change in the photolysis. The photolysis effect could be, but you're not completely sure about that, is right? You're not
No,
completely.
I mean, when I looked at removing aerosols, what was the impact on ozone? There was probably an increase by about 20% of ozone once you get rid. And that was just a chemistry. It didn't have any impact from photolysis or changing the product.
So it could be important.
And it will be increasing ozone if you get rid of aerosols.
Okay, here a plot taken in fact from Daniel also showing, of course, this you know that. But what I wanted to point out here is that the air pollution-related greenhouse forcing is probably about of the order of 2 watts per square meter. If you take the tropospheric ozone, the black carbon, and the methane changes that have occurred, which is relatively important. And you can see also that the cooling from scattering anthropogenic aerosol might be important too. So there is a need to highlight, of course, that air pollution has an impact on the forcing and probably on climate. So I wanted to look now at the other direction. Yes? Back?
If by some means you produce scenarios for the next 100 years,
For these things here.
for these things, yes. So for tropospheric ozone, for methane, and whatever. What do you lose then by not running the chemistry with the climate model going forward compared to just taking those scenarios for those gases and running the climate model without
I
chemistry?
understand. Well, what you lose, of course, is basically, you're doing basically what has been done with CO2 in the past, where CO2 was increasing. Then people say, oh, wait a minute, the CO2 is itself affected by the climate change, and now the CO2 that you assume without feedbacks is wrong by, some percent, 20 to 200 ppm in year 2100. Could the same thing happen with chemistry? So before I can answer that, I need to get back to my second part here and raise a number of...
So I should ask the question again.
At the end, yeah. Look, but I will tell you, the return loop, looking at the return loop. How does climate change affect the composition of the atmosphere? Well, there are many ways by this. First of all, you might have the potential for more frequent, stable, or blocking conditions, and therefore perhaps some more frequent heat waves. But we don't know yet exactly, but if that happened, we could have a severe degradation of air quality, and even though it might not be important as a feedback into the system, it has some societal implication. People believe that in Europe, when the 2003 heat wave came up, a large fraction, I don't know if it's most, but a large fraction of the people died from excessive ozone concentration above 150 ppb, which is much higher than we have. More frequent wildfire in a warmer and drier climate could enhance emission and could also, of course, lead to degradation of air quality. And if we have more precipitation, that would go the other way, of course. But there are many, many other aspects. But just as
an aside, I was always curious about this. What is about ozone that kills somebody?
Lungs. It's an oxidant. Well, your eyes, if you go in a very high ozone, you will start. Your lungs, if you have a heart disease, a heart, condition, it's an irritant. Yeah, it's an irritant of your lungs.
So it doesn't.
Asthma,
So it just makes it harder.
It's
for
an
your
oxidant.
body
It's a
to-
very aggressive oxidant. Very aggressive oxidant. It will, of course, there are other aspects. For example, the productivity of crop will reduce, and some people calculate that one ppb is so many million in California, and these kind of. I don't know the numbers, but some people do that. But generally speaking, what you see is that the probability of daily ozone pollution increases dramatically through temperature, and that has to do, of course, because of chemistry, but also perturbation in transport. I mean, a number of people are looking at this more importantly. But now what I would like to discuss are other mechanisms that are the return loop, if you want, that will help us trying to address your question. For example, what happens to methane emissions if we have climate change? Just like we ask ourselves, what happens to CO2 if we have climate change? Well, in the case of methane, you know that the natural emissions is about 200 teragram versus the anthropogenic ones, which are 300 teragram. So that's about the division, the separation between natural and anthropogenic emission. But in terms of the wetlands, people believe that by 1 degree Kelvin increase in temperature, the emissions increase by 20%, which is relatively important. But we don't know quite because we don't have a lot of measurements to really characterize that number. So it's a bit of an uncertainty. What is perhaps more important or interesting for climate is the potential, if the permafrost disappears in particular, is the release of methane hydrates that are locked into the permafrost or also locked in the ocean that could dramatically increase methane in the future. And that would, of course, then return back to climate forcing. So to what extent will it happen? I think it's still very, very uncertain. This is here just to show you some field measurements that show the methane flux from wetlands represented here against temperature. By the way, there is a paper recently that suggests that methane is also released by the vegetation. It's still a very open question, but that could also have a temperature dependence. If we look at the organic compounds, such as the isoprene, which is precursors of ozone, perhaps also precursors of aerosols, and we look here at the red line, we see a large change here of the emissions as a function of the temperature of the leaves, and for some other VOCs of biogenic origin, it might be even a stronger relation. And that, of course, is a potential for feedbacks between climate and chemistry. In fact, Alex Günther was mentioned earlier, I think by Phil, has established emission inventories for present day and also for future climate. What scenario it is here, I kind of don't remember, but what you see here are pretty large differences, and they could have influence on both aerosols and also the ozone concentration. It's been discussed already that biomass burning emission could change. Biomass burning is important for a number of ozone precursors. It's 50%, maybe a bit less, I say 40% of the CO emissions, 20% of the NOx emission, 8% of the methane emissions. And if we have more fires, of course, these emissions would increase. And of course, climate change could lead to some of these increase in fires. If you look at lightning, for example, we now believe that the production of NOx by lightning is between 2 and 20, more likely 5 teragram of nitrogen per year. Well, it's important for the ozone budget. Some models suggest that a 1% increase in temperature could lead to 5 to 15% increase in lightning. In fact, we have the specialists here in the room who could say more than that, but it could also have an impact on the chemistry of the atmosphere. Same thing with emissions of nitrogen oxide as well as N2O by soils. They are changing as a function of temperature, soil moisture, so we could expect changes with climate, but these are not very well, in fact, they are very poorly quantified. Emissions of dust, emissions by the oceans are other climate-sensitive processes. Just to go a bit quickly, the dry and wet deposition, the intensity of the deposition could be modified if we have, for example, different precipitation patterns and intensity. And some people have been trying to quantify this. This is the increase in methane from wetland and tundra, the increase of NOx from lightning, the increase of DMS from the ocean between present time and 2030. I think it's again based on the IASA scenario. Now, the increase of water vapor in the atmosphere that we expect when we do climate prediction has an impact, of course, on many compounds. And there are people who have been looking at this. Again, this is for 2020 here, not 30, or is it 30? No, it's 20. This is the difference between a case where climate change is considered and climate change is not taken into account. And you have a number of compounds. Now, this one for non-chemists might be a bit mysterious. This is PAN. PAN is an organic compound that carries nitrogen oxide. It's very stable if it's cold, but if the temperature increases, it will decompose and release nitrogen oxide. And you see here, for example, that nitrogen oxide will increase dramatically in a region where PAN is decomposed, especially at high latitude. This is the change in OH that is calculated. This is just the effect of climate. And I'm going to pass this, but of course there is an impact on ozone. Usually you have decrease of ozone due to climate in the region of the ocean. You might have increase in other regions due to increased emissions by isoprene, probably biomass burning, and also increase in lightning. But all that is very, very poorly quantified. Now, we should not forget the stratospheric feedbacks into that. We expect in the future decrease in stratospheric temperature, which means that we expect a decrease in the ozone destruction rate, except in the high latitude regions where more polar stratospheric clouds would be present under a colder stratosphere. So that could lead, generally speaking, with perhaps generally speaking, people believe that there will be more stratospheric ozone and therefore an increase in the stratosphere, downward motion. There should also be, according to the models, an increase in the Brewer-Dobson circulation, and that could also modify the stratotropic change with an increase in tropospheric ozone. What seems to be now the consensus from at least the last WMO ozone assessment is that climate change would lead to a more rapid ozone recovery. Okay, quickly a few things on feedbacks, and I took here the ozone cases. Again, if you look at tropospheric ozone, it depends on many things. The intrusion from the stratosphere, the precursors that photochemically produce ozone, of course transport also, and this depends on emissions and deposition. But if you now introduce climate change, you will affect a number of those parameters, the emissions, the chemistry, the transport, the deposition, and so on. And this is, for example, here, according, to our model here, which basically is the model, when I say ours, is some work I did with Martin Schulz in Germany. This is the change in temperature, assuming a doubling of CO2. This is the change in water vapor, assuming also doubling in CO2. And this is the calculated change in the NOx production from lightning, which is an increase of, I think, about 30%. When you look now, if you do a prediction for ozone change, which, by the way, is most pronounced in the tropics, as you can see, in year 2100 compared to 2000 using the A2 scenario, this is the case without climate feedback, and this is the change with climate feedback. And you see that in this case, at the surface, future ozone increase is lower than it is here, and in fact we have a decrease that is more marked when the climate feedback is taken into account than when it is ignored. And this is due to the fact that you have more humidity and more destruction of ozone, but this is not the case everywhere. You see here the decrease due to the water vapor increase. This is an increase in ozone associated to the increase in lightning, but this is very model dependent, and I'm sure other people find different results. So,
sorry, one big difference between those maps seem to be over the oceans. Is that the?
Yeah.
Is that to the water
yes,
vapor?
because this is why you have the impact of increased water vapor that is probably dominant. Lightning.
Emissions increasing over.
You've
got isoprene emissions.
Yeah, emissions increase over the land,
yeah.
and lightning increases also mostly over land.
Is the
Is it a local increase in the, is it the water vapor increase at the surface that results in a change in the concentration at the surface, or is it
everywhere?
Everywhere.
The effect of lightning is larger than the effect of exchange in the stratosphere.
Yeah, in our case. But you know, the British model shows not a lot of change in the NOx, except that I think in their case the clouds penetrates further in the stratosphere, and they have an increase in NOx really almost in the lower stratosphere, really at the tropopause, which it's a bit different from our results. So in terms of the processes that can be considered here, well, they're listed. We talked about them: biomass burning, salts, NOx, lightning NOx, natural methane emission, natural VOC emission, and so on. And you can see that some have a potential to have small effects, some have a potential to have larger effect, and the one in red, so climate-induced change in stratosphere tropospheric change, lightning, natural methane emission, natural VOC emissions. In all these cases, they have a positive feedback element. Now, I should go quick. How much time do I have with this interruption? I lost track.
Well, given the break, maybe 10, 15 minutes.
Okay. So what I didn't mention now is a potentially important aspect that happens through the biosphere. In fact, the biosphere is affected by the chemical state of the atmosphere, and the biosphere will also, of course, affect the carbon cycle, which affect climate. And so examples are the fertilization of the biosphere by iron. I think Phil mentioned that. Also, the deposition of nitrogen and ozone on the surface could affect the biosphere and therefore the climate system. This is here a model that shows basically how the ocean primary production is changed when you include the basically the deposition of atmospheric dust. And there is an interesting effect here. And of course, the question is, when the ocean primary production is changing, what does it do to the carbon cycle? And so we have to put all the pieces together. The nitrogen deposition associated with nitrogen fixation is important in relation, of course, to food production and so on. If you look at how things have changed in terms of the grain production, the meat production, and the energy production, it has been very substantial to maintain, for example, to the use of fertilizer here, to maintain sufficiently food to feed the world population, of course, the energy production associated with industrialization. And so the fixation of nitrogen, in other words, the conversion of N2 into other form of nitrogen, which is shown here as a natural fixation, and then here the anthropogenic fixation, has, well, the anthropogenic effect has changed dramatically. It's probably now larger than the natural processes. As a result of that, if you look at the global nitrogen budget, and I'm just putting here, in pre-industrial time and present, you see large disturbances in this nitrogen cycle. And basically the global nitrogen budget is really out of balance now compared to what it used to be. One of the impact of that is that the deposition of nitrogen has increased dramatically, and it's clear that it's important for the carbon cycle, but it's also intimately related to atmospheric chemistry. And so taking the famous and infamous graph that Peter Cox has been putting together, which I like very much, I think what all this shows us is that if we not necessarily want to predict future climates, I'm still coming to your question, but if we want to look and understand how the system works, we have to consider, the climate being part of this. But of course, the climate is affected by aerosol, by greenhouse gases, the chemistry, composition, the ecosystems, And all the interactions that are indicated here need to be taken in what will become Earth system models. And then we can look at perturbation from the human system through emissions of greenhouse gases, of reactive gases, aerosol, to land use changes, to fires, but also to things like irrigation and urbanization, which are shown here. And that means that full treatment of the climate chemistry ecosystem land surface needs to be constructed to really estimate the importance of all these relation and interactions. So, question, finally, do we need chemistry in climate models? I think, you know, that in the long term the CO2 forcing will dominate to a large extent what we can expect. Not necessarily beyond 2100, but at least in the next century. However, there are a number of uncertainties. The impact of methane, for example, is uncertain. Future methane trend is a major unknown, as I said. The possible release of methane from permafrost region could be huge. You know, what's going to happen in the Arctic in particular. The treatment of methane requires certainly a wetland models to see how things will happen, and also a model that deals with the permafrost and its evolution, and also needs to account for trends in OH. Changes in air quality, which might not be the goal of the climate modelers, but might be an important aspect for society in response to climate change, is also important. And we know that a warmer climate will probably have a different air quality. And the stratospheric ozone recovery, which is another problem of interest to certain people, will also be affected by future climate change. Now, the reason the question is asked is because of the cost of chemistry. And so what I believe is that, you know, if we start talking about typically 50, 100 species, which is what we have in the models these days, the computational cost is high. It's very high, in fact. And nobody...
That was 1,500 species? Is that what you said?
No, no. 50 to 100. No. I had to fight with Sasha Madronich when I came 12 years ago at NCAR. He wanted 8,000 or something like that. So this will never work. So I believe that one way to go here to investigate the importance of these feedbacks, which I think is associated with a lot of unknown and potential important perturbation, is not to just go, you know, by the brute force and put the 100 species in CCSM or in other Earth system or climate model. But it could be done by several ways. One would be to try to develop smaller, reduced chemical scheme. Now, I don't believe very much in those, because I believe that the errors that you do when doing that, is probably not very different from just ignoring them or specifying the chemical species, since chemistry is not a major feedback factor, probably. But what I think could be done is to work through time slice. And you could have a offline chemical transport model on the side that has all the complexity that you need to, for example, calculate OH. And then say, I'm going to ask this, and well, what you could do is to add one compound, namely ozone, that is transported in your climate model. It is a tracer, so you would transport it just like you do for other tracers, but you would need to get the production and destruction rate from photochemistry, and that you would get from your offline model maybe once every 10 years or so. And then you would enter that into your model, assume that it's not changing very much over 10 years, and rejuvenate this production and destruction every 10 years, giving you an OH also, and maybe other compounds that you need, H2O2 if you want to do the aerosols, the sulfate aerosols, and just have your chemical transport model, which is expensive, running at certain intervals. And these intervals could be 10 years, It might be every 20 years for pre-industrial time where the chemistry was less important. It could be every 5 years when you're in a region where changes are extremely rapid. So yes?
But with that, you probably wouldn't be able to do air quality.
You could do it in your chemical transport model, I think, to which you can start nudging a regional model if you want to go to very high quality. But you could do it in your. Well, we should talk about that.
So what you're proposing now is you don't have chemistry running in the climate model.
Right.
But you stop the climate model
You stop the climate
every
model.
10 to 20 years.
You provide your winds, temperature, humidity, and all climate variable. You send them to the offline chemical transport model. Those guys run a year. Maybe they do it twice to be in certain equilibrium. And then you bring that back you bring the production and destruction of ozone, plus maybe the zonal mean OH that you will use for your methane destruction. You might need H2O2 for your aerosol, these kind of things. And then you go on for 10 years.
For the stratosphere, especially in the northern hemisphere, the interannual variability is high. I mean, very high. So is that going to be a factor in doing this?
I believe that most of the interannual variability for ozone, for example, is associated with the dynamics and changes in the dynamics. That would be calculated by the climate model.
No, but does it, I mean, supposing a quick year when you have a cold vortex and you do your production destruction in that regime, I mean,
yeah.
That's an issue, isn't it? I mean, because after all, ozone is high or low depending on whether it's cold or not.
It is an issue, but the only other alternative is to put everything in the climate model.
We have, basically following your approach, we have two atmospheric chemistry routes. One is online chemistry, in which we try to use as simple a chemistry as possible, and lack of the higher order hydrocarbons probably influences the result negatively and makes the result poor.
For the troposphere.
For the troposphere. And one in which we provide to the GSChem model at Harvard the climate model output, and they then run with 125 species, 150, whatever they're doing, for air pollution purposes. That's what they're doing. And what we found was that we started with Harvard actually doing it online and doing it with these time slices and linearly interpreting between. And basically, we didn't really find all that much difference from doing it offline versus doing it online. Right. And so it became, and they wanted to add more and more chemistry, which meant that the computer time went way up. Yeah. So offline, the one problem with offline, obviously, is they want more and more things saved at a higher frequency for air pollution. So eventually it starts weighing you down to have it as save everything, every time step in all these regions. And when you go in to find a resolution, that will just amplify the whole process. So there's no free lunch here.
So I believe that this is something that the working group could discuss further.
I might mention one thing you could use from integrated assessment modeling is some analysis from the other side. For example, the NOx emissions in many of the SJS scenarios are not realistic, as the newer scenarios have much lower emissions because they didn't include air pollution controls. That's something to keep in mind. But even when I've included the air pollution controls, I really don't know if they're enough. You know, I can think of a consistent scenario in terms of income. You know, higher income, people aren't going to tolerate pollution events as often. But I need to know, did I get it right? You know, in different regions, there's going to be different relationships, and then there's these transboundary issues. So we could really use some more analysis of that as an input to see whether we've got the right ballpark on NOx or not, and how methane affects that, and so on.
Okay. I think I'm almost done. What did I say here? Yeah. My point here was that, you know, even if chemistry is not a major amplifier or damper of climate change, although it would be interesting to find out for methane if that wouldn't be just the same thing as for CO2. There is still interesting science to be done here, and not everything is IPCC, and there are other aspects. There are also a lot of aspects on the regional dimension with important social consequences that are important. I think the evolution of the Arctic is a very important issue. What's going to happen there? We see the ice melting faster than we thought. What about the fate of the Amazon? We talked about all that, I think, this morning. So I think these regional questions, which have global links, are also important to look at. I had a few remarks that were a bit outside to finish. And of course, you have all seen this becoming more and more complex. Perhaps in the future, we will have operational Earth system model that will be used in conjunction with observation from space and other means, models that will include the atmosphere, the ocean, land, the biosphere, that will unify it, the water cycle, the carbon cycle, to really have a predictive tool, not necessarily for long-term runs, but to basically monitor and predict the short-term evolution of the entire Earth system. So that's something that a number of people are considering, and that's another reason for having probably a number of, not only the pure climate, physical climate aspect, but hydrology, very detailed, air quality, very detailed, and so on.
As soon as you say predictions, doesn't that mean you have to initialize it correctly?
Yeah, they would be initialized things. So that is really related to having a monitoring system. And that's exactly what GEOS, this system of system, is trying to accomplish. So this is why I'm saying observation are key in trying to basically have a monitoring and short-term predicting capability. The kind of things in chemistry that we do is now this chemical weather prediction, in other words, air quality on the global scale. ECMWF is now getting extremely strongly involved in that through the GEMS project. Canada has done a lot of work, others, US also. But again, these are short-term things. Now, by the way, I just put here the number of flops that are needed to look at that, and clearly the computer aspect to that is also important.
When you say short-term, what do you mean?
10 days, a month, a season, maximum.
Yeah, because I look at that, and I think a lot of the things that we've been discussing as challenges are non-issues over that time scale. Like vegetation dynamics, forget about
No,
it.
that's right.
And you initialize, so you don't have to worry, your errors are smaller for that. It's a different way of operating the models.
So doesn't the problem simplify enormously if we
Well,
shorten
but
time scale?
the people want to do that, want to look at the carbon cycle and the seasonal evolution of the carbon cycle. If you have an El Nino, what's going to happen to CO2 that, in 3 months and these kind of things.
Yeah, my only point is that we may sort of have the capability for that almost already. It's not the big questions are in the long-term evolution.
Right.
But this would also be an optimal way to initialize a decadal prediction system. Right? And if you had the same physics in it, so it had the same carbon cycle, you would nudge internal parameters that ought to give you better predictive capability on a decadal timescale as well.
Maybe, but the processes are different.
You'd have to include the processes that are on the longer timescale to do that. Yeah.
So I wanted to make a pitch because not only for the climate issue, but also for the chemical composition of the atmosphere, the human dimension is important, and clearly we have to think about how to bring together the global biogeochemical system and the socioeconomic system. And that's, of course, another challenge. We don't discuss it here, but my point was that as we really want to bring together Earth system model, it's not only the atmosphere, the biosphere, the ocean that is part of the Earth system. This is the natural capital, but you have the human-made capital here. It's what some people call the anthroposphere. The natural capital brings ecosystem services to the anthroposphere, but then the anthroposphere impacts the natural capital. And how do we do that? I think it's a very difficult issue. Perhaps the first step is really to take the problem from the issue of land use change, and we have now sufficiently sufficient detailed land surface model that probably, you know, here we could see climate almost as an input, as a forcing, as well as CO2 change and the land use change. We could start really bringing the human dimension into this Earth system model, because that has an impact not only on the climate, but also on the composition of the atmosphere. And looking at how the chemical composition has been affected by land use change, I think has never really been done. So, challenges for the future. I took those 3 bullets here, not from anything related to geosciences, but from the Max Planck Society, who has been trying to look at how its science should be evolving. And you will see that it fits very well to what we are doing. Interfaces between the micro and the macro worlds, in other words, across scale interactions. Interface between the living and the dead nature. This is exactly how to link the biosphere with the physical climate system or the human dimension. And an interface between nature and culture, which is perhaps the social system and the natural system. Thank you.
The general response of the community was to sort of disbelieve all of that, and to note that the ice core measurements of methane were not consistent with those sort of methane releases. So I think there's a lot of skepticism about the types of temperature changes we've seen, even during the glacial era, 5 or 4 degree warming, being something that could trigger methane releases. Now maybe 4 or 5 degree warming from now would be different from the glacial to now.
Yeah, but there were time periods, like around the Permian, for which methane pathways seem to be a very, very strong candidate.
And the PETM,
yeah, that's right.
Do you think that the initial value problem approach of the system model, right? Like incorporating satellite data into the model and assimilating such data, do you think that that kind of activity leads to the improvement of the model? Well, eventually it should.
Well, I think that because we will work very closely between models and data by doing this, we will probably understand some of the functioning much better, especially the short-scale questions. But of course, I don't believe that the people who are putting together these programs do it necessarily to improve fundamental science. In fact, there's very little component in the science of these programs. You know, when you say, well, there are questions, well, we just want the data, we want you to do prediction, and the science should be done somewhere else. So I think they do it primarily because they believe that it has a high economic potential.
Can I ask a slightly different question? When we do runs over the 20th century, many of them have been done now, and they show that if we don't get the correct volcanic emissions and variation in the solar output, then we do not reproduce very as well the climate of the 20th century. What do we do in future scenarios for volcanic eruptions and changes in solar output? When I asked somebody that a few weeks ago, they said we don't do anything. Is that correct?
No.
What is done?
I think in the IPCC runs, nothing was done. For the solar cycle, you might perhaps predict 1 or 2 cycles ahead. So you could take that into account, and you know the period. So you know that you might be wrong a bit on the amplitude, but you know there will be an 11-year cycle. So you could put, you know, kind of a constant 11-year cycle, not knowing which one will be high and low in the future. For the volcanoes, no strategic plan of any organization has ever put a prediction on what it would happen. But I think
system model.
I think, you know, because you don't expect the geologists to tell you when the eruption will take place, either you neglect it or you might put, you know, do sensitivity tests once in a while, put a a volcanic eruption in 2050 that is, I don't know, Espinatubo, and then see what happens.
We don't do that. So there is a slight offset between the
right.
industrial to present day on the future.
Yeah.
Yeah.
But
so I don't know.
I believe there are efforts, for example, Casper Amman is working with several other people to actually stochastically generate a frequency of volcanoes.
Yeah, I've seen that. So that's another way, is to use...
But if we're thinking of actually doing what you call predictions of the future, one or two big eruptions,
NASA,
really throw that out?
NASA claims that they will predict earthquake by 2020 or 2030, and so if they do it, they might also do the volcanic eruptions, but I doubt it.
How far
it's also likely to be less
predicted?
Like I think
next week?
Yeah, I think they were, these were short-term predictions. So I don't think any anybody, but they are.
No, but we're talking about maybe using 5, 10, 20 times as much computer time to do these short predictions and get a volcano and one big volcano to predict it.
Yeah, but although you can't predict the volcano itself, you can predict its climatic impact, right? Right, it's gone off, which is also the
what I can tell you is that both the Hadley Center and in Hamburg also now, they are doing, have been or are doing supervolcanic, super volcano, and I think Caspar is doing that too. What would happen if Yellowstone, explodes at a rate that is 1,000 times Pinatubo or something like that? Land would change completely. It would be covered by ash, and the ocean would be deeply perturbed. For how long, it's unknown, but it would be an interesting problem to look at. Using these kind of Earth system model, the chemistry would be, of course, very, very strongly perturbed.
The problem is that when you look at the ice core data and you try to estimate what the volcanic eruptions were as a function of time, and you look at things like Tambora or the big eruptions in the past, and then you try to look at the paleoclimate reconstructions, the bigger eruptions did not seem to necessarily be associated with more global cooling, even the eruptions that we know were global. So then there are issues as to whether the bigger...
It's a very short period of time, so did they see it?
It's a short period of time, but so the direct forcing component does not seem to relate as strongly in the observational record to the magnitude of eruption. And so people have said, well, maybe if you have bigger volcanoes, the stuff coagulates and falls out faster. And you can see it's very clear in the ice core record. There's no correlation between the magnitude of the volcano
and the temperature.
Good
point.
Thanks, Keith.